Swayam Prabha. Digital India. Educated India.
Right. So, now with this now we can begin the topic of nonlinear optimization, which is now our most general optimization problem, which is where we have, say, you are minimizing some function f over a set say S. Right. Now, what we need for this sort of problem is to say find a very general condition, so that which characterizes a point x star for that is a local minimum. So, suppose x star is a local minimum, suppose x star is a local minimum, then we need a condition that this sort of x star must satisfy, a necessary condition for this sort of x star. Alright. So, now this condition is given through what is called the tangent cone of the set. So, I will define this for you. What is a tangent cone? So, the tangent cone at a point x star for the set S is a collection of vectors D such that there exists a sequence xk lying in S, xk converging to x star, and a sequence say tau k that is positive. So, it decreases to 0, such that D can be expressed as this limit. D can be expressed as the limit xk minus x star divided by tau k. So, the tangent cone is those vectors D for which there exists a sequence xk in S converging to x star, and a sequence tau k of these are scalars, okay, positive scalars converging to 0, such that D can be written as in this form. It is the limit as k tends to infinity of xk minus x star divided by tau k. Now, what is so can you make a before we see what this set actually means, can you make a few simple observations? Do you see that D must be the set T x star S, okay, this tangent, what we call the tangent cone, do you see that this must be a cone? It is it's very easy to see that, because if I look at a scaled version of D, that always exists in this set, because all I need to do to construct such a D would be to just simply scale the tau k appropriately, right. So, if I look at say alpha times D, then if I want to get alpha times D, all I have to do is divide the tau k by alpha, and that will give me alpha times D, right. So, the tangent cone is always a cone. Always a cone. Now, what does this set look like? But it is a cone, but what sort of set is it? So, to get some intuition on that, let us try to see what this particular thing, which is the limit of xk minus x star divided by tau k, what is that actually saying? So, suppose I have a region like this, and suppose let's begin here. Let's suppose this is my point x star. Now, what is this? So, this is my set S and this is my point x star. So, now for this sort of point, what is the tangent cone? So, this is a point x star that lies in the interior of S, right. So, x star belongs to the interior of S. Okay. Now, in this case, what is the tangent cone? Now, the tangent cone, if you look at the definition, what it says is, well, it is those directions D such that you can construct a sequence x k converging to x star and a sequence tau k going down to 0, such that D can be written as x k minus x star divided by tau k. Now, x k minus x star, so if here is my point x star and here is my point x k. So, x k is a sequence that is eventually converging to x star. So, it is a sequence that approaches x star. So, here is the vector x k minus x star, right. It is a vector, I can think of its origin shifted to x star and pointing towards x k. So, here is my vector x k minus x star. X k minus x star, as x k goes to 0, sorry, as x k goes to x star, x k minus x star will go to 0, right. But what about x k minus x star divided by tau k? What would happen to that? Where would that end up pointing? So, suppose let me amplify the picture here. Suppose here is my point x star and here is the sequence x k that converges to x star, right. Here is suppose x 100, then x 1000, etc., and eventually it comes, eventually these are the various x k's and they eventually converge to x star, right. So, the distance x k minus x star or the vector x k minus x star, that vector is eventually going to become 0. But if you look at x k minus x star divided by tau k, where would that end up pointing? So, the way to think of this is that you can think of tau k as keeping track of time in some sense. So, and x k is a trajectory, it is a point that is moving and it is eventually converging to x star. Tau k is keeping track of time. So, since x k converges to x star, the numerator is going to 0, but numerator divided by time would be what? It would be the rate of change, or equivalently it would be the tangent to this particular trajectory, right. So, x k minus x star divided by tau k as k tends to infinity would end up pointing along this sort of direction, the limiting direction by which you approached x star along this trajectory. So, if for instance you did, so here was x star and you did something like this, suppose you did this and eventually came along eventually approached x star along this particular direction, the limiting value of that direction, something like this, is where that D would end up pointing. And of course, because this is a direction, you can always scale it. You can measure time in any units. You can always scale the axis of time, and that will give you a longer arrow and a longer vector D. That is why this is a cone, right. So, this every direction, every D in the tangent cone is a direction from which one can approach x star from within from within S. While staying within the set S, the directions by which you can approach x star is that the set of such directions is the tangent cone. Yes. 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 So I was about to come to that question. Good. So now come back to this question. So suppose x star is in the interior of S star S. So x star lies in the interior of S. Then in that case, what would be the tangent cone? Then it would be Rn, because you can approach x star from any possible direction or any direction, because the entire ball in Rn can be fit inside the set S. So you can approach direct radially along any direction towards x star from inside the ball, right. So if x star belongs to the interior, then is a subset of, so then this is, then the tangent cone is equal to Rn. The Rn is the ambient space of S, right. So what this means is that well, for points in the interior, this the tangent cone is given trivially. It's always Rn. Now what about what if the point is somewhere here? So what if you have if the point x star is now here on the boundary? Then what would be the tangent cone? Now every direction, so if you are on the boundary and you have, if the set has an interior and you are on the boundary of it, and it is possible to approach from the interior to the point x star, then all such possible directions will be in, all of these possible directions are included in the tangent cone. And you can keep including directions that just graze past the boundary of the set. And you can keep doing that till the point where eventually you actually become just tangent to the set. All of these are possible directions by which you can approach the point x star, right. So if you are, so let me just draw this more neatly. If your point x star is here on the boundary, right. So then this, all of this. So in short, this entire thing here would be the tangent cone, all of these directions. Right. But then it's a little more complicated because of some reasons, and I will explain to you what the reasons are. See, let's suppose you take this sort of set. Suppose here's my set S. Now a point here in the interior, we know what the tangent cone is. So my set is this box in R2. If I have my point in the interior, then this point, the tangent cone is just R2, because I can approach from any direction. Now if I'm here, then what would be the tangent cone? It would be this particular half space, right. It's this half space, because I can approach from all of these directions. The half space formed by this face of my box. Now what if I am here at this corner? If I am at this corner, then actually the tangent cone would then be these two. This particular, so this cone here would be my tangent cone, right. So now the reason this has changed is because in both cases you are on the boundary. Okay, in both cases you are on the boundary. all right. Here on when you are on this boundary, you have exactly one tangent to the set, whereas when you are at this boundary, what is the tangent to this set? There is no, the tangent is actually not defined. What you have is tangents to this set, this particular surface, and tangents to this particular surface. And from there we are trying to somehow get to the tangent of at this corner point, right. So you have to be a little, this is where the complications begin to arise, that so if you have a simple if you have just a in simplest of cases, it does happen that you can think of, you can just draw a tangent at that particular point and try to get the tangent cone by looking at the tangent. But if you don't have differentiability and so on at that of the boundary at that point, then you end up having problems with in defining in visualizing the tangent cone, right. So I'll give you more examples of why this why the tangent cone is a very deceptive object. So if you have just a simple, if you have only, let me give this on this side and start on a new page. So suppose let's consider something like this. So suppose we have suppose I have a circle, this is my origin, okay, a circle without the interior, and I consider a point on the boundary. Now what is the tangent cone for this point? It is only the tangent plane, right, only this particular plane, that would be the tangent cone. If I have a circle, but with the interior considered, and I take this point out here as my point x star, then so circle with the interior, then the tangent cone is this half plane, half space, right, the half space on that lies on this particular side, the side on which the circle lies. Okay. Now suppose I did the following. Suppose I have one circle here, okay, and suppose I took another circle like this, okay, and I included, say, the interior of both. So I have this interior included, this included. Now all of these points here that I am marking shading with red, they are now part of both circles. So let us call this set S1, let us call this set S2. The red region is part of both circles. So if I take a point here, suppose, or if I take a point, let us begin with a point like this. So take a point here, what's the tangent cone at this point? At this point, tangent, okay, tangent cone with respect to what set? So we are looking for the tangent cone at, so with respect to the common region, with respect to the set S1 intersection S2. Okay. So this point belongs to the common region. What is the tangent cone at this point? It is again going to be this half space. Okay. What is the tangent cone at this point? So if x star is this one, which lies on the boundary of both circles. So what you might visually you might be able to figure out that, okay, well, I should be looking at this one, I should be looking at this one, and let me take the intersection of these two, the common region between these two, and the common region would be this. So that would give me the tangent cone at this point x star, right. So by looking at examples like this, you are led to sort of thinking that this is actually the same as doing, effectively just same as doing tangent cone of the intersection, you would think is equal to equal to this. The intersection of, you will just look at individual sets, look at their tangent cones, and then when you get to a point that lies in both, look at the common part of the tangent cones of the two tangent cones. Okay, but you will soon see that this fails miserably. Okay, so let us consider this. Here is one circle and here is another circle that touches this circle at exactly one point. Okay, here is my, so these two circles are tangent to each other. Here is my point x star. So and I am including the interior of the circle. So this is my set S1, this is my set S2. So now what is S1 intersection S2? S1 intersection S2, they intersect at only one point. Then my S1 intersection S2 is just the point x star. Okay. Now what is the tangent cone at x star of S1 with respect to S1 intersection S2? It is 0, only the vector 0, right? It is always a cone, so it has the vector, only the vector 0, because there is only one point in the set, xk is equal to x star, so you are always going to get 0. But now what if you did your intersection formula? What would you get from the intersection? So you look at the intersection, so here is the tangent cone with respect to S2, and this on the other side is the tangent cone with respect to S1, right? And you take the intersection, what you would get is just the tangent plane. So if you look at T of x star with respect to S1 intersection T of x star with respect to S2, that is equal to the tangent, the entire tangent plane. At x star. And what has happened here? The intersection of individual tangent cones has turned out to be much larger than the true tangent cone. Now you can see this can very quickly get slippery. So when you have multiple surfaces intersecting, it is not possible to get to the tangent cone of the common region by just looking at each of them individually and then taking the intersection. It is possible that you will end up getting a larger set in that way. Okay. So this is one of the key reasons why study of tangent cones you need to do carefully. There is another reason also. I will come to that. I will come to that in the next class. But the main sort of slippery part of tangent cones is this. Okay. Now, why do tangent cones play such an important role? And I will state the result for you. It is not that hard to prove. The reason they play such an important role is in optimization is the following. So suppose, so here is the main theorem in which they appear. So suppose x star is a local minimum of this optimization, minimizing f sub x in S, then you must have that grad f of x star transpose d is greater than equal to 0 for all d in the tangent cone. So the gradient of f at x star transpose d is greater than equal to 0 for all d in the tangent cone at x star with respect to S. Okay. The proof is very easy. So the proof is, so suppose suppose it is not the case. Suppose this is not true, then in that case there exists a d in the tangent cone such that transpose D is less than 0. Okay. Okay. Now, D belongs to the tangent cone. Since D belongs to the tangent cone, you can, there exists your sequence x k converging to x star. So, x k in S and a tau k decreasing to 0, such that if I look at tau k d is equal to x k minus x star plus something that is small o of tau k. We have seen this notation before, the small o notation. Small o just means that small o of tau k is a quantity which when divided by tau k also goes to 0, right. So, tau k d is therefore equal to x k minus x star plus small o of tau k, all right. So, what, and moreover by Taylor's theorem, f of x k is equal to f of x star plus gradient of f at x star transpose x k minus x star plus small o of norm of x k minus x star. So, now if I substitute this in, I would get that f of x k is equal to f of x star plus gradient of f at x star transpose d into tau k plus something which that is small o of tau k. So, the small o of x k minus x star, I put that in, that will then become small o of tau k, right, by substituting. So, after substituting this here, I get that this is equal to, so f of x k is equal to f of x star plus gradient of f x star transpose d in tau k plus something that's small o of tau k, which means that f of x k is equal to f of x star plus tau k times grad f of x star transpose d plus small o of tau k divided by tau k. And now, small o of tau k divided by tau k is a quantity that, this is a quantity that goes to 0, and since the first quantity is strictly negative by assumption. So, by assumption the first quantity is strictly negative, the second quantity is going to 0, which means that eventually for large enough k, so let me just complete it here, for large k, f of x k would be less than f of x star. But then x k converges to x star, which means that if x k is converging to x star, and but for large enough k, f of x k becomes less than f of x star, then it cannot be that x star is a local minimum. So, this is a contradiction. Right. So, this is a contradiction. So, so which means that this must be the case. So, if suppose x star is the local minimum of this, I forgot to write here, f belongs to C1, so that is differentiable, then we must have that grad f transpose d is greater than equal to 0 for all d in the tangent cone. So, you can see here this is a very general purpose condition, any set, any function, so long as the function is differentiable, it must satisfy this. But the problem that we encounter is that if often our sets are defined using the intersection of multiple sets, and we do not know how to get to the tangent cones of the intersection. Okay, so that is the next thing we need to sort of overcome, and then we will be able to write out optimality conditions for optimization problems. Okay. Okay, so I will end here now.